Now let's start with the session 5, the sequences, continuation of the convergent sequence, whatever we proved in the previous sessions 4 and 4a. Now the continuous of that theorem 4, we are going to, in this session, we are going to solve for or prove the theorem 4 and 5. So let's take up theorem 4. If limit n tending to infinity xn is L and L is greater than 0, then there exists a positive integer m such that xn is a positive quantity. This is for all n greater than m. So this is a limit. This is the limit and it's a positive quantity. Whatever it's going to converge, whatever the limit is there, it's a positive quantity. This is for all positive integer m such that we have to show this. So let's start proving this. So what do you know? L is a positive quantity. If L is a positive quantity, what will be L by 2? Excuse me. What will be L by 2 is also a positive quantity. We do agree with this. Now we know by the definition limit of n tending to infinity xn is L. That is, there exists some m belonging to n such that modulus of xn minus L will be less than L by 2. Yes, of course, it should be less than L by 2. L is a positive quantity, L by 2, and L by 2 is within L. So, of course, the positive quantity, the modulus sign, whatever we take, should be less than L by 2. This is again for all n greater than m. So, now let us write down the expansion of modulus. So, it is minus L by 2 less than xn minus L less than L by 2. This is for all n greater than m. Now adding plus L throughout, so what do we get? L minus L by 2 is less than xn is less than L by 2 plus L. This is for all n greater than m. So what I am getting here, L minus L by 2 is L by 2 is less than xn is less than 3L by 2. This is for all n greater than m. So from this what do we get? From this inequality we are able to get that xn is greater than L by 2, which is a greater than 0. It is a positive quantity, therefore for all n greater than m. Therefore xn is what? Is a positive quantity. This is for all n greater than m, and hence we have proved the theorem 4. Now let's start with theorem 5. If in a convergent sequence, in a convergent sequence, a finite number of, I am choosing a finite number of terms from that convergent sequence. So I choose them and I remove them, are removed. Then what happens is the convergence of the sequence will not alter. Even if I take out the finite number of terms and remove it from the convergent sequence, the convergence of that sequence is not going to alter. So this is what we are going to prove in this theorem. So proof. Let's start this proof first considering the convergent sequence. So what is this? This xn is a convergent sequence. For limit convergent sequence, we know the definition. Limit n tending to infinity xn is L. Now let the first, in this sequence, let me remove the first m terms. Removing the first m terms. I am going to remove the first m terms from the convergent sequence. So after removing, what I am going to get? X of m plus 1, comma x of m plus 2, etc. x of m plus n, etc. It continues. The sequence continues. So now the terms remaining in the sequence are only this. Now I have to show that this is also a convergent sequence. So what should I show? To show that this sequence is convergent. I need to show that this sequence is convergent. Now we know, since from the definition we know this, we know what? The convergent sequence. So limit n tending to infinity xn is L. This is for all epsilon greater than 0, some positive quantity. And for all, let me take capital M belonging to n such that modulus of xn minus L is less than epsilon for all n greater than capital M. So this satisfies from the definition of the convergent sequence. Now we know that n is greater than m. That means m plus n should also be greater than m. Already this is a greater number. If I add one more thing, of course it is a greater number. Now let me write the modulus for this. So what do I get? X of m plus n. Okay. Minus L is less than epsilon. This is for all m plus n greater than m. Yes, we agree with this, right? In place of xn, we are taking m plus n minus L less than epsilon. This is for all m plus n greater than n. Now here x of m plus n minus L is less than epsilon for all. Let me take for n and shift the other m to the other side, small m. So what do I get? M minus m. So what I am getting? N is greater than this quantity. So it is satisfying our convergency condition. So you can write that therefore limit n tending to infinity x of m plus n is L, and hence the sequence is convergent. So this proves theorem 5.